Can anybody online just confirm that you can hear us okay? They're going to be bashful.
I hope so. I mean, there's only one person online right now. Two people online.
I want people online.
You are.
Yeah.
Oh, okay.
Can you hear me? Yeah. Hello, okay. Test. Yep. Okay.
Okay, you're good to go.
Perfect.
Looks like you're good.
All right. So welcome everybody to the Cincinnati Observatory. My name is Wes Ryle. I am the astronomer here at the observatory. I was formerly a faculty member over at Thomas More University and taught there for 16 years, which is how I got involved with Kentucky Area Astronomical Society. This meeting is the first time where I'm running as president. Dirk Gruppe from Northern Kentucky University is serving as the current vice president. And so we'd like to welcome you on the behalf of the observatory and Northern. And of course, we are co-hosting this event, and pretty much everything today will be here on site at the observatory, and then tomorrow we'll be over at Northern Kentucky University. Just some kind of logistics. We have water and coffee over here because I know I couldn't have the coffee too far away from Dirk or else he would go crazy. There are additional beverages over across the way in the other building, as well as snacks over in the other building. I did that intentionally because I'm evil and I wanted to, if people want snacks, they have to go over and see the posters. And so some of you have already set up your posters. If you just got in, the posters are over in the other building. There are push pins and clips in order to mount posters over there. We've got a few different poster sessions scheduled in between the talks. And I'm hoping that folks will go over there and interact with everybody who's presenting the poster when they get a chance. In addition to the posters, obviously we've got a 15-minute break here at the beginning, a half an hour break later, and then a little bit of a half-hour break right before dinner. Dirk was saying that if we want to do kind of a tour, a historical tour of the observatory, we'll probably just save it to the end of today, right before dinner. Yeah. Yeah, because Dirk, we've actually coerced him into becoming a volunteer here at the observatory. So he's an official volunteer. He gives presentations to the public, but also leads the tours and things like that. And if any of you all are local and are interested in becoming Cincinnati Observatory volunteers, that's something that we're always looking for, and always looking for new presenters, especially for people who have an astronomy background.
And the other thing is we won't be able to observe tonight. So if you want to get to an observing night and you want to get this for free, well then become simply a member, which is $40 for individuals and $60 for families. And the good news is not only that, you get 10% off in the gift store. So if you saw the little plush planets out there, if you want to buy all of them, you basically get one for free at the end of the day.
Yeah.
So you want to become a member.
See how well trained he is? Yeah, very. Yes. The other thing, we mentioned the possibility of observing after dinner. If folks wanted to observe after dinner, it is likely going to be cloudy and maybe sprinkling a little bit, so I don't think we'll get a chance to observe. However, if you're paying attention, you are paying attention, you know that splashdown happens this evening shortly after 8. And so after dinner, if anyone is interested in coming back to the observatory to have a watch party for Splashdown, we can have it on this screen or the screen over in the poster presentation area. Probably this room would probably be easier if we wanted to watch Splashdown together. Splashdown itself, I think, is scheduled for 8:07, but of course, re-entry starts, maybe about 20 minutes or so before that. And so if you get back to the observatory around 7:30, we can all tune in and watch together. Just a little bit of background about the observatory, just real fast. I did put this on, okay. This is the oldest professional observatory in the United States. Oh, yeah. Oh, in the Americas altogether, true, yes, yeah. And so it was really unique start in the sense that it was basically crowdfunded by the citizens of Cincinnati. Our founder, Mitchell, had basically started giving public lectures about astronomy. And because of the interest that he generated, he was able to convince the folks and the public of Cincinnati to invest in $25 shares to basically build the observatory and find a telescope, a world-class telescope to have here in Cincinnati. The telescope that the observatory was founded around is over in the other building. It is an 1845 Mertz and Mahler telescope manufactured in Munich. And when you get a chance to see that telescope, since I know that you all have a physics background, be sure to look at the inscription on the base of that telescope. That telescope, the lens was designed by Fraunhofer, and you'll see his name inscribed on the base of that telescope. That telescope turns 181 this week. And so it's one of the oldest telescopes in the world that you can actually still look through and still view through and still use. And we use it for almost every program we have. The newer telescope that we have upstairs in this building is a 1904 Alvin Clark and Sons telescope, 16-inch as opposed to the 11 and some change for the one over there across the way. And so we'll give you a chance to see both. But again, the weather's probably not going to cooperate in terms of viewing, unfortunately. Let's see. I was trying to think of any other question or any other things. The other cool thing, obviously, it's a little bit inconvenient just to have this kind of seating for a conference because we're all used to having our laptops out in front of us. But we wanted to actually have the opportunity to be in the observatory just because it was kind of a unique opportunity, a unique location. This very room, as you might tell, even actually used to be an observatory itself. The cement piers here are actually where there would be meridian telescopes. And this whole entire length of the ceiling and along the walls here could open so that they could see objects as they transited the meridian. There's some pictures of those original meridian instruments right over there. In 1940s, when Paul Herget took over as director, he took out the telescopes of this room because it was at that point kind of obsolete. And he actually filled this room with early IBM computers because from the 1940s all the way up into the 1970s, the Cincinnati Observatory served as the Minor Planet Center. And so if you paid attention to asteroids and minor planets, right, it's currently at Harvard, right, that controls the Minor Planet Center. But for many decades, the Cincinnati Observatory is basically where all asteroid observations came through, calculations of orbits and all that kind of stuff. If you get a chance today, feel free to browse around the museum area there to take a look and learn a little bit about their history. And of course, Dirk will also be able to talk about it. Dirk and I will be able to talk about it as part of the tour a little bit later. Can you think of anything else? That's true, yeah. Yeah, Dirk was around back in 1845, right? Yeah?
No, a little bit more on logistics. So when you come, please park in the parking garage. Hopefully the gates will be open. If they are not and you need a parking pass, let me know. I can give you a parking pass. It's a short walk over to the Science Center. We are on the second floor of the Science Center. So you come out of the parking garage, left turn, walk to the Science Center, go to the Science Center, go up the stairs to the second floor, and it's in room number 201. So hopefully you will find it. If you have to pay for parking, that's pretty much it.
Oh yeah, and so yeah, tonight we've obviously got snacks over there if you get hungry during the day. Tonight is kind of dinner on your own. I sent out in the last email some dinner recommendations, in particular some places that have lots of parking and lots of seating, kind of communal seating, because that's the only harsh thing about being in the Cincinnati metropolitan area is that usually parking is at a premium. And so there are a couple of recommendations for big places. Of course, you can go wherever you want. And then again, come back if you want to. And then lunch tomorrow will be covered by the meeting. We've tried to keep these meetings as cost-effective as possible, obviously free for all of you all. And we've been pretty successful about it so far. And this is, I think, the biggest meeting that we've had so far.
This is the biggest meeting.
Yeah.
When we had this meeting, we said, oh, yeah, we'll have 25 people on Friday. Saturday, so already 24 on Saturday. But then we got 40 people. Yeah. And that means we cannot have bigger. Yeah. So this is the usual story. We have about 40 people coming from usually
Right, exactly. As far as logistics for the talks go, if you have your own laptop and wish to use your own laptop, that's fine. You can hook up to the HDMI via either the HDMI or a USB-C adapter up here. You'll need to be signed into the Zoom meeting and share your screen as part of the Zoom meeting. If you'd rather just load it onto the laptop that we have here, the communal laptop up here, you can do that as well. For the first session, we might need to have some people load up last minute. But if you get a chance during the breaks and you know that you're presenting later and you want to go ahead and load up on the communal, that's fine. But again, using your own laptop is also fine too. We've got different chairs that'll try to be in charge of timing. I'll give, for example, I'm chair for the first session, and so I'll try to give a 5-minute warning, a 3-minute warning, 2-minute warning, 1-minute warning. Ideally, your talk's about 12 minutes, and then followed by about 3 minutes for questions. Any questions before we get started? If you do need restrooms, you'll go out to the lobby and down the stairwell, kind of curve off to your left. It's just a onesie here in this building. There are also restrooms over in the other building, kind of in the door and to the left as well. Okay. We do have Wi-Fi. It should be the public one should be available. You'll have to click a little checkbox in order to kind of get through, but otherwise it should be open. If you have any difficulties, let me know. Okay. Actually, so I switched it around a little bit because we had somebody who was arriving a little bit late, and so we were going to wait and do little 1-minute poster previews at the end of the session. I'm sorry, I didn't actually update the or I sent out the wrong schedule with the email, of course, even though I reviewed it multiple times. And so I think first up, we have Matthew Bayless from the University of Cincinnati.
Oh, let's wait before we apply. Let's not assume we're going to like what we hear. It's very kind. Okay, I think I've got it.
It should be okay to share your screen.
Yeah. And let's just clip some ticket. That is my play up song, actually. That's whenever I give a talk. I do prefer that be the music. Where is the thing? Sorry. There we go. Okay. Got to get the order right here. Let's do the whole thing and play the whole thing. Okay. Got to get this out of the way. Okay, I think everyone can see what they need to be seeing now. Oh, nice. It's a classic pointer. Excellent. Okay, well, thanks for having me. Thanks for letting me go first. I had some scheduling difficulties this weekend, and it's a long story, but I kind of have to run right after this talk to administer antibiotics to a 3-year-old now, so it's yay. I'm not contagious. Ear infection. Okay, so I'm going to open up here with a talk about my own research these days, which is heavily focused on using gravitational lensing to study distant galaxies. There are a few students from my group that will be talking later, so I'll advertise their talks. And a lot of what I'm going to be doing here is laying the groundwork and then promoting some recent results by some collaborators who've gotten some pretty cool papers out as part of our collaboration. I'm old enough now that I don't really do a lot of this paper writing myself. I just I have opinions and I give talks. So yeah, this is what we're trying to do with lensing: is take galaxies apart and put them back together again. It's kind of a fun artsy title for saying we like to magnify, use lines of sight where we have highly magnified distant galaxies, allowing us to zoom in on scales that you can't normally resolve in the distant universe. I guess we'll just point and click. There we go. So to put this in context, we have astronomy has a long history of studying how galaxies evolved across the history of the observable universe. And the most common way we do this is in deep field, so-called deep field studies. This is a James Webb Deep Field from, I think, the JADES survey, where you just take one of your best telescopes and stare at a relatively small spot in the sky for a long time, and take really beautiful, really uniform data studying the entire population of galaxies you can see in the image. And we can see tons of galaxies. These are just like zoom-ins on little individual systems. And I've done it this way because this reflects really the industry standard, which is to study galaxies across cosmic time using galaxies as like the de facto unit. We make plots of like the mass metallicity relationship, like galaxy by galaxy, like luminosity functions, counting galaxy by galaxy. And we've learned a lot, right? This tells us a lot about the average evolution of galaxies across cosmic time. We learned a lot about how on average galaxies build up their metals, how on average galaxies form stars and those stars age. But if you actually want to get into the physics that drives those individual processes, like how stars form out of giant molecular clouds that collapse under gravity, how stars explode, how stars blow winds out into their immediate surroundings, you can't really do that on a galaxy by galaxy scale. You need to resolve physical scales that are smaller, which you just can't do at the sort of most wavelengths in the distant universe. And so that sort of motivates the use of gravitational lensing as a complementary tool to take, not samples of thousands and tens of thousands of galaxies, but smaller representative samples of galaxies to use as laboratories to study subgalactic processes. And that's what myself and my collaborators have done a lot of. And so just to introduce a lot of what we do, we've got kind of a poster child system here. This is a gravitational lens galaxy at redshift 2.5, where you see 3 images of the galaxy, right? So it's multiply imaged. Each image is highly magnified, in this case, about a factor of 30 or so. And if you reconstruct what this galaxy looks like in the source plane, this is actually an outdated reconstruction, but it's close enough. You can see that there's a small structure, like a clumpy structure that shows up here on the sky, gets mapped back into a D-lens source plane where you can measure the size of that clumpy structure. So this is just one system we showed off in 2017. I want to highlight that lensing does 2 things, right? So it's for get into the physics very briefly. It's literally an aerial magnification effect. It's a zoom in. So it conserves surface brightness because it has to conserve energy, which means you can do 2 things, one of 2 things, but not both at the same time. You can either zoom in on small sources. So you can view like high surface brightness small sources resolved on small angular scales. In this case, size is down to like 10 parsecs at redshift 2.5. Or you can count up all the light from the thing and gain like a big signal to noise boost. So you can either resolve smaller structures or you can gain signal to noise. You can't do both at once without violating the laws of physics. My collaborators and I have really taken an angle where we try to have our cake and eat it too into both of these things. And we do that by studying some of the brightest lens systems we can find. And so most of the systems you'll see in this talk and that we work with are giant arcs like this that were visible in very shallow ground-based imaging. So this is shows up in a 55-second integration from the Sloan Digital Sky Survey, which is a 2.5-meter telescope. So these are really, really bright things, high surface brightness things, which means that when you resolve small structures, you have intrinsically high surface brightnesses, which gives you good signal to noise. And then when you count up the total flux, you get really extraordinarily fantastic signal to noise. And this is a little bit different from there are other intelligent approaches where you use lensing to push detection limits, identify the faintest galaxies. That's not what we're doing. We're trying to study the brightest things in both integrated and spatially resolved ways. And a lot of the work we're doing these days is a part of this LEGOS collaboration. Lensing Galaxies Growth Structures is the name, which is PI'd by myself, Gaurav Kuller, and Michael Florian. It's really an amalgam of many collaborations that have already existed, all the same people for the most part, where we have essentially over several cycles collected James Webb Space Telescope data on a sample of about a dozen highly magnified lens galaxies. I guess it says 10 there, but these days a dozen is a slightly more accurate number, giving us in total hundreds of hours of James Webb time, which allows us to perform really detailed, high-resolution and multi-wavelength studies of these highly magnified distant galaxies. And so I mentioned 2 students, Lena Eby and Cole Panzer, are going to give talks on the projects they've started in the past year or so with me using these data. But today I'm going to highlight just a few of the really cool results that some of the more senior members of this collaboration have been putting out to show off kind of what we can do. And so, early James Webb data, ERS was just early release science. It was kind of cycle 0. Really, it was the first stuff observed in cycle 1. We had some lens galaxy studies that came out in that cycle. We want to highlight just some of the cool results where we've got really mature stuff that can be shown off. So this is one of the galaxies in the LEGO sample. It's redshift 5, so really our highest redshift system. There's a cycle 1 program PI'd by Gaurav. This is called the Wazark because it resembles a moderately famous Disney character, which you try not to get in trouble for. Once you've seen it, you can't not see it. It's really amazing. And so this is a ground-based image. This is a shallow ground-based image. This is from the decals. So this is now a 4-meter telescope. It's still a couple minute integrations. Just ground-based imaging taken uniformly across the entire sky. This thing is pretty honking bright. If you go and look at what this thing looks like with Webb, you see an extraordinary diversity of structure and color, right? So this is exactly what we want to get at with these lens galaxy studies. We want to see that on average, the galaxy might have some average color, have some average, some total stellar mass, et cetera. But individually, we know there's quite a diversity of stellar structures, star-forming regions, nebular gas inside that thing. And so the Webb data, Webb's really the perfect tool for them. It's the perfect tool for a lot of people's science. But Webb's the perfect tool for this, just because it allows us to do spectroscopy and imaging across a broad near-infrared wavelength range. In this case, mostly near spec, so 1 to 5 microns, though we have some cases MIRI data too, extending out to like 20 microns. Really broad wavelength near-infrared studies of these things in the distant universe, again, in both imaging and spectroscopy. And to motivate the taking galaxies apart and putting them back together element of the talk, I want to highlight just this sort of morphological plus photometric modeling we have to do for these systems. So because you're resolving lots of structures, there's just lots of individual little clumpy things, right? A little star-forming clump here, a little star-forming clump there, maybe a diffuse sort of halo-ish looking thing there. We build morphological models. This is with GalFit and PyCirsic, and we use a number of different packages just kind of to test consistency. You can go into these systems, you can literally build a model of every single resolved structural source in the image, including describing both its extent, its size, its morphology, and also its brightness. And so you can take, in this case, I think this is actually Hubble data, not the Webb yet, but Hubble data of this system, build models in each of these bands, subtract the model from the original Hubble data, and get a residual that's essentially 0. The only residual that's awful here is actually this thing, which is the foreground lens, which we're not so concerned with. But this is a really beautiful, this model is doing a really beautiful job of capturing the flux and the structure of this thing, which allows us to truly identify all the different pieces that make up this galaxy. Now we do this, not just in imaging data I mentioned, but also spectroscopically. So with Webb, you can take images of the sky, but you can also put down, in this case, what's called an integral field unit spectrograph, a box that takes spectra of every little piece on the sky, and you can essentially take spectra of everything within this sequence of white IFU boxes, right? And so this allows you to not just study how these things look in imaging, right? What are the photometric broadband properties of the little structures, but to extract full-on spectra of individual structures. So what's been shown here, and this is from Taylor Hutchison's, well, this is from Borov's paper. Most of the work I'm going to get into first, this plot is from Taylor Hutchison's paper. I guess the source plane is from Borov's. Is we're pulling out spectra of just 2 particular clumps in this galaxy. Something we'll call clump 3, which is this little red knot up here. Something we'll call clump 5, this little blue knot down here. And you've got your really beautiful, in this case, rest frame optical, because it's redshift 5, spectra of these 2 very distinct and extremely different star-forming regions, or well, I should say stellar populations within this distant galaxy. So it's just kind of an example of what we can do. So Taylor Hutchison is one of the real heavy lifters in our collaboration, data-wise. She's at Goddard. She knows about as much about near-spec James Webb IFU data reductions as anyone I've talked to. She's been pushing nebular line studies using the IFU data in these galaxies. And so what she's shown here is spectroscopic maps of this galaxy that are isolating particular emission lines from nebular gas. There's actually quite a few pixels here that are empty. This is because this galaxy actually turns out to be relatively old. It doesn't have a ton of super excited nebular gas, but it still has a fair bit. And she can go into these data and measure sort of classic nebular diagnostics. For those who are really in the industry, O3, O2, essentially the ratio of how much doubly versus singly ionized oxygen there is, which is telling you something about how strong of an ionizing photon field there is. You have lots of ionizing photons, you make a lot of O3. If you have fewer, you make a lot of O2. You also need higher energy photons to make O3. So you're learning something about the stars that are ionizing the gas when you look at ratios like this. And you can see this like variable heat map that you get across the galaxy. This quantity can be turned into something physically more interesting, which is log U. Not super obvious what that is, I guess, unless I explain it. And that's essentially the flux. It's essentially the quantity of ionizing photons. So how many ionizing photons are being produced per unit time, which makes sense, right? This was sensitive to ionizing photons, and this sort of can be translated into an ionizing photon flux. Anyway, and so the real note here is that you can talk about global galaxy properties. She's showing like the median and the global properties of this galaxy you'd measure if it was just a typical deep field galaxy. And then you can see the true astrophysical spread of log U values within this galaxy, right? That a global property, an average, right, that you measure, like a flux weighted average, tells you something about the galaxy, but it doesn't at all capture the range of properties that are within this galaxy, really the diversity. The same thing is true of other diagnostics. These are just other diagnostics that are proxies for measuring metallicity, right? So these are the actual line diagnostics. This diagnostic maps to metallicity. This one maps to metallicity via a different scaling relation. This is a third diagnostic that maps to metallicity via a different scaling relation. Same thing, you can measure global median properties of each of these metallicity indicators and then look at the spread. And you see huge differences, right? You see tight relations, like basically certain line ratios, in this case into H alpha, one of the historically most heavily used metallicity estimates, that's really, really tight and not varying across the galaxy. Other metallicity measurements that are varying quite dramatically, which is telling us something about how, in this case, it's telling us something about how our assumptions about the gas that we're observing when we measure these lines are maybe not the best. That we'd like to think in the ideal world that we're measuring gas in H2 regions around stars. Stars ionize the gas. We thus measure the properties of the gas and infer what's going on with the stars ionizing. However, there's also other gas distributed around galaxies. A lot of it's called this, oh man, that's unfortunate. This diffuse, can I drag to move the word drag to move? Well, that says DIGS, D-I-G-S, diffuse interstellar gas. This is gas that's not in H2 regions. It's the stuff that's in between H2 regions that's mostly shocked. This can be from stellar winds escaping into the ISM, supernova remnants. They can have a lot of different, can show up in a lot of different ways. But the contributions that this diffuse interstellar gas makes to different nebular line strengths is going to push around what you actually measure. And it's going to bias things away from what you would measure from pure H2 regions. So cool result by Taylor. Goroff has done a similar study in this galaxy, but focusing now on just the pure stellar populations, not so much the nebular lines. We can go and we can say, well, the nebular line emission, Taylor's been working on that. Oh, yeah, we'll see. Been working on that. Well, I figured, it's, you got to open, never mind. All right, so Taylor's focusing on nebular line emission. Goroff's focused on the continuum here, which is the direct result of all the stars across this galaxy. And because this thing is so bright, with Webb, we can take this, in this case, it's an R1000 for those not in the industry. That's a moderate resolution, and at redshift 5 and in the infrared, really, really spectacular resolution and high signal noise spectrum of this galaxy. And we can fit models of what kinds of stars make up this entire galaxy. And in those models, you can recover the star formation history. Like, when did the stars in this galaxy actually form? When you do that, you get something like this, like a look-back time plot where you say star formation rate as a function of look-back time. Here is now. This is, what, 1 billion years before redshift 5, which I think is actually non-physical. I think the universe started somewhere around here. It's good that it's 0. And you can say, when did these stars actually form? And you can see that there's a complex history here with stars forming, the star formation rate dropping, coming back up again, then kind of deadlining to 0. One of the big things we'd love to be able to do in the distant universe is make this kind of measurement for tons of galaxies in deep fields where we cannot resolve the spectra. What we can test with lens galaxies like this is we can answer the question, when we do this kind of modeling using the integrated spectrum of like the entire galaxy, do we get the same thing as if we take apart the individual pieces and do the same modeling on all of the individual components and then add it together to form, to reconstruct the star formation history? And so this is what Goroff is doing in this galaxy. You can take, I've just like highlighted here, I guess, 10 individual star forming regions within this galaxy, or stellar populations within this galaxy. The spectra from these regions, color-coded, are shown here. You see a huge diversity. Anything with emission lines, that's still residual star formation. These are passive old galaxies. So wide range of stellar population ages being represented here. And then you can basically map these back to say, which clumps are mapping back to which episodes of star formation in the history of this galaxy, which is an extraordinary success of the stellar population modeling effort. So this is one of my favorite things I've seen like in my career. This paper is very close to not being preliminary, but being out. But I'm not allowed to say that it's out yet. Other things we do with Lens Galaxies is another Cycle 1 program. I'm not going to talk about a lot of the results from the Webb data. I'm going to show you there are these 3 papers. I think now actually very recently a 4th, maybe 5th have popped up. This is studying a Lyman continuum leaking galaxy that is strongly lensed. So Lyman continuum radiation is what ionized the universe, which means redshifts like 6 and 10. We don't really know how efficiently it was created, and we don't really know how it escaped galaxies. And so lensed systems like the sunburst arc here allow us to study in detail how that process occurs, how the ionizing proton production how the ionizing protons are made and how they escape. So what's shown here are non-ionizing UV emission in these bands, in F814. So every F814 is just like, that's stars. And then ionizing photon production, escaping ionizing photons, I should say, is shown in F275. So this is super high energy photon. What you can see is that ionizing photon production only comes from this one clump in this galaxy that is multiply imaged 12 times. So you have a whole huge galaxy, ionizing photons come out of one small channel in it. My postdoc, who's at Cincinnati, now he's got another postdoc position at Caltech, performed a spatially resolved study of how this one Lyman continuum leaking clump differs from the rest of this galaxy, and showed that it really is an outlier. That if you take really any region, this is an entire complete image of the galaxy, any region of that galaxy that's not producing ionizing photons, and measure its properties, in this case, its ionization, lionization, that's that O3O2 diagnostic we talked about before, how many ionizing photons you have. UV slope is essentially how blue are the stars. you see that the images of the Lyman continuum leakers all populate this very particular space. They're really offset, they're very distinct, they're very different. And if you make, in fact, an image of this galaxy, where instead of showing flux, you show the value of this UV slope beta, so just how steep is the slope of the UV spectrum, the leaking knot shows up as this like ridiculous hotspot that's like on the order of like a few, maybe at most 10 parsecs in size. So this is really showing us that, you know, ionizing photon production, and in particular its escape, we see as a super local process. This is not a galaxy average process, right? This is something that's happening on really small physical scales that correspond to like feedback, pushing, blowing out channels in galaxies and allowing those photons to escape. You can also look at Lyman alpha properties. This is work by, yeah, that's right, a former Cincinnati undergrad. I don't know why it's taking forever. Riley Owens, he's now in grad school, where he used ground-based data of the same sunburst arc, targeting the different regions. And he was focusing on the Lyman alpha emission line profile in this galaxy. That's what's being shown for each of these 8 spectroscopic slits. There are 8 Lyman alpha curves with, you see a huge diversity, right, of shape. You see this triple peaked shape coming from regions where Lyman continuum photons are escaping. You see this, just what we'll call like a red smooth peak occurring everywhere else. And Riley used our lensing knowledge of the system and these spectra to basically reconstruct how the Lyman alpha radiative transfer is spread across the face of this galaxy. So these are just 4 reconstructions of the galaxy in the source plane, and the red lines are 4 of the spectroscopic slits mapped back into the source plane. And the spectra of Lyman alpha from those 4 slits are shown over here on the right. You can see that, you know, the slit M5 is the farthest from the leaker, shows just this like relatively simple red Lyman alpha peak. As you get closer to the peak of the leaker M4 and then M6, you see that central peak start to appear. And as you get even closer in slit M3, which is the thing that doesn't hit the leaker but comes the closest, you actually start to recover that triple peak profile. You can assign, you can recover sizes, like what's the extent of these different Lyman alpha features. That the blue wing is kind of a 100 parsec scale structure. The central wing maybe 200, 250. And then once you're beyond that, you're down to like a simple sort of red wing. Lyman alpha radiative transfer is deeply complicated, but also very important, and one of the most valuable observational tools we have at, say, redshift 6 to 10, actual epoch of reionization, for understanding how reionization happened. So Riley's work here is really showing us something about the scales on which it's operating at high redshift, which is really cool. Oh, so that is the end of my talk. Hopefully it didn't go over by too many minutes. I just want to kind of summarize some of these high-level results that we're getting. I also want to, again, advertise Alina and Cole's talks that are coming up, that are coming out of the same collaboration. I mentioned that we've got, you know, more work kind of on the way, and apologies for going slightly long. Thanks. I aspire to answer all questions in advance by anticipating them in the talks. It's okay if there's no.
Just on the instrumentation there for the spatial results that James Webb.
Yep. Yep. The IFU is indicated. The size of the IFU is this little white box. It's a 3 by 3 arcsecond IFU, 0.1 arcsecond pixels. In principle, you can recover scales smaller than 0.1 arcseconds. In practice, that has proven to be extremely challenging. But yeah, it's essentially this is a 3 by 3 arcsecond box, and it's divided into 30 by 30, so 900 total spatial elements, and you get a spectrum from each spatial element. And so you can the pixelization here is what you're seeing, right? Each of these little pixels is literally an IFU. This guy, yeah.
But like you said, that's a spectral resolution of about 1,000.
In this case, yeah, you can do. There's a low resolution prism that its resolution varies quite a bit with wavelength. There's low resolution prism, R of 1,000 grading, and an R of 2,700 grading. In this case, yeah, we've got, this is the R of 1,000 data. We've got some of all of that, but yeah, it's yeah. Is there a? I don't know if I'm just telling you weird facts or if there's something else you wanted to get at with the question. Okay, yeah. I will say in this case, the R of 1,000, it's really hard to do at high redshifts. Higher dispersion, lower signal to noise typically for a given surface brightness. The high surface brightness here is what gives you this R of 1,000. And the power of these data, you see all these are, this is your Balmer sequence absorption series, right? This is your Balmer break. I mean, you've got actual stellar absorption lines resolved at high signal to noise. Like this literally is the noise array for this system. So it allows, I mentioned at the start of the talk, we want to do good measurements on small regions that are high surface brightness, and truly spectacular high signal to noise measurements of integrated quantities. This is an example of the high signal to noise integrated measurement.
Does Pixar have a hold on the lens work? Because I noticed yours looks a whole lot like the 8 o'clock arc.
Oh God, the 8 o'clock arc. Well, they all tend to, in some respects, all arcs tend to look similar because self-similarity of large-scale structure, I suppose. Structures are usually vaguely round, and the typical mass distribution results in like an archy structure. So they've never made a legal move that I'm aware of, to get at your real question. I mean, there's a famous one that you'll see around called the Cheshire cat lens. That's our Hubble data, by the way. That was a good one that came out of Sloan. Let's stop sharing.
Stephen, are you ready?
Okay. And I am leaving, but I'm not hard to find. I live in Cincinnati, and I can grab this. So if anybody loves what's going on here and wants to talk more, just always email me. The worst I will do. The worst I can do is be incredibly busy.
There's an HDMI on.
And we didn't know that the top left slider there. Put that all the way in. And are you sharing?
No, I should do that before the slideshow. Get everything organized here. So that. Ooh. This is fun.
Yeah. Feel like you have the power.
Yeah. All right. So my name is Stephen Reek. I'm a third-year PhD student at the University of Cincinnati, so very local here. I'm representing sort of the cosmology contingent of our department. My advisor is Jesse Muir, who's here today. A number of us here from Cincinnati are working in cosmology, but I think I might be the only one presenting. So you get me as a little intermission between the more typical intergalactic astrophysics folks. My first project that I've been working on for almost a year at this point is seeking optimal nonlinear scale cuts for beyond lambda CDM galaxy clustering and weak lensing analyses. I'll first provide a bit of background on all of those things, sort of in reverse order, starting from our observational data that we'll eventually be working with, talk about what I mean by beyond lambda CDM cosmological models, and then talk about the scale cuts. Then I'll talk about our procedures for evaluating them, finding optimal ones, and then talk about where we're going with this project, which is still in its relatively early stages, and sort of summarize, and then that'll be the end. Come on. Arrow keys didn't work for a second there, but we're good. So we are working with photometric galaxy surveys. This means telescopes that take images of the sky through a number of color filters, which means we don't have specific redshift data from spectroscopy, but we're able to image orders of magnitude more galaxies. The dark energy survey, which will have its final analysis published later this year and has some results already out, is on the order of hundreds of millions of galaxies. The upcoming Legacy Survey of Space and Time, or LSST, by the Vera Rubin Observatory should be starting later this year and will image basically the entire night sky that it can see every few nights. And it'll do that for 10 years. So there'll be a huge quantity of data coming from LSST. It'll see, I think, on the order of billions of galaxies. For all of these galaxies, we really only care about their positions and their shapes. We're using these as our probes of cosmology because both of these tell us about the matter distribution in the universe. Galaxy positions tell us about that because galaxies form in overdense regions, and their shapes tell us about the matter distribution along our line of sight to those galaxies because of weak lensing. Not the really dramatic lensed arcs we were seeing in the previous talk, but just slight distortions in the shapes are actually able to be detected when you're working with numbers of galaxies this large to learn about the matter distribution. Specifically, we're not looking at any specific galaxies, but looking at the statistical properties of these entire galaxy populations. Specifically, we're looking at 3 two-point correlation functions. You'll often see this abbreviation 3 by 2 point analysis. This is what that means. that there are 3 different 2-point correlation functions for galaxy positions and positions, positions with the shapes, and shapes with the shapes. With that data, what the ultimate goal of cosmology is to come up with some cosmological model that best describes and predicts and explains all of the data that we see through various sources. Large-scale structure is just the one that we care the most about for my project. So far, the best model that we have is the lambda CDM model, which I'm sure you've all heard of before. It has only 6 free parameters, features a cosmological constant representing dark energy, and dark matter of some unknown nature. It also assumes the standard general relativity as our theory of gravity. But this lambda CDM model might not be the best. We don't know. We want to test various extensions to it. Some ways you can modify this standard model is introducing features that lead to a different expansion history, like changing the nature of dark energy, or changing it in some way that leads to different growth of structure. We see this cosmic web on very large scales in the universe. This is affected by things like the matter content of the universe and the theory of gravity. There's different ways to modify general relativity that would result in different clustering features. For all of these models, we need to be able to accurately generate theory predictions of the observed data to compare with the data that we see, to be able to place constraints on our models. The key ingredient for that, for getting these 2-point correlation functions predicted from our theory rather than from the data, we need to use this thing called the matter power spectrum. The matter power spectrum is the correlation function of the Fourier transformed density contrast. So we define the density contrast here as sort of the density in some location divided by the average density. So this tells us how overdense or underdense that region is. We can get its overall statistical properties by doing the writing a correlation function for it like this, specifically in Fourier space, so that rather than caring about specific locations, we can look at all of our data and learn about how matter clusters on different scales. So this is a plot of the matter power spectrum in K-space here. So these are smaller scales at higher wave number and smaller scales at lower wave number. Computing this matter power spectrum is very easy when the density contrast is small. You can do that calculation analytically. So we can do that for any model that we want to test. But getting the matter power spectrum on smaller scales when the density contrast starts to become large is a lot more difficult. For the standard lambda CDM model, we have ways to do this. Different tools calibrated against n-body simulations, things like that. But those are very expensive and time-consuming to produce, and thus aren't available for all of the models that we might want to test. The key question of our project is, when you have some cosmological model that can't accurately make theory predictions with those nonlinear density perturbations, such that you basically only have the linear theory for your smaller scales, you lose the behavior from these nonlinear effects, from that addition to the matter power spectrum on small scales. When you don't have that, how do you protect against bias from those unmodeled effects? You want to sufficiently be able to protect against bias while still preserving the most information. It could be easy to just completely get rid of all of these scales, but then you're reducing your signal to noise ratio tremendously by just not including data that you want to include as much of as you can. What that looks like so far and has looked like historically, namely what the dark energy survey analysis did, was use this delta chi-square scale cut method. This is also a sort of subsample of the data. So to explain that a little bit more, this is a galaxy-galaxy correlation function, so position and position autocorrelation of our galaxy sample. For just one of the redshift bins, specifically this is the second one, this is only 1/40th of the full 3x2 point data vector. So there's 39 more plots like this, but I'm not going to overwhelm you with all of those. We can just look at this one as a representative sample. You can see that there's a difference between the linear and nonlinear theory predictions for lambda CDM. We already remove a bunch of data points due to baryonic cuts. We aren't able to model the baryonic physics on even smaller scales than we care about for the nonlinear effects. And so those are removed from the analysis regardless. That's a whole different person's job, whole different project than mine. What we're looking at is how do you do these nonlinear cuts in the best way? Because you can see even after the baryonic cuts are applied, there's still a significant difference between the linear and nonlinear data points, particularly that adds up when you're looking at all 1,000 or so data points. So the way that you figure out how to accommodate for that difference is you calculate this sort of uncertainty-weighted difference between the nonlinear and linear theory predictions, weighted by the data covariance matrix. And then whichever data point contributes the most to this delta chi-square quantity, you remove from the analysis. You proceed removing points one at a time until you've removed enough that this delta chi-square value is below some value. Namely, your theory predictions should match the linear theory predictions so that you can analyze a model that isn't able to predict the nonlinear theory. Hopefully that made sense. It got a little twisted there. So how we're ultimately going to do that, like our project outline structure is we will specify some galaxy survey. So far, we've only done this for DES year 3 because all those analysis choices were already made and very easy to implement quickly. We'll eventually be extending to forecasts for LSST and make recommendations for that future survey analysis. You choose some cosmological model. So far, once again, we've only done lambda CDM because it was the simplest to implement. But ultimately, what these tools will be used for is models beyond the standard model, like those that modify gravity or modify matter in some way, like the presence of sterile neutrinos. From that, we are able to compute derivatives of the data with respect to the model parameters. So like if you change one of your cosmological parameters in some way, how does that affect your data? We're able to answer that question in a very simple way using the code that exists. You need the expected data on the expected uncertainty on your data covariance matrix, and some nonlinear perturbation. So far for us, we're just using the lambda CDM nonlinear perturbation. Basically what the difference is between the linear and nonlinear theory predictions for lambda CDM. That's our nonlinear perturbation. With those ingredients, we're able to use Fisher forecasting, which is a methodology for forecasting the expected parameter constraints from an experiment without actually doing a full analysis and without actually having real data. And so because we're concerned about a survey that hasn't happened yet, this is really useful. It's also very quick computationally, which means we can look at a whole bunch of iterations really quickly and get the things that we are interested in, namely what the uncertainties on the parameters will be and how much bias there will be in the cosmological parameters, converting from this nonlinear perturbation to the data to some shift in the parameter values. Then once we have those results, we will be able to apply different scale cuts or different other ways to mitigate the bias from unmodeled nonlinear effects to all of these ingredients. We'll be able to use these results to evaluate those. And so far, we have some preliminary results already for the DES Year 3 Lambda CDM sort of simulated analysis we've done. Both of these are sort of different ways of displaying the same information. Here, this is the parameter bias computed from the Fisher forecasting, weighted by the uncertainty for that parameter. I'm only showing sigma 8, which characterizes how matter is clustered, and omega m, the matter energy density in the universe, because those are the two parameters that are best constrained by this type of analysis. The x-axis here is the number of points removed due to those delta chi-square scale cuts to some threshold. I'm showing these vertical lines for 3 different thresholds. You can see if you don't cut any data points, you clearly have significant bias, like more than 1 sigma in sigma 8, and that's no good. If you go all the way to the DES threshold of 1, you're definitely very well protected against bias, but to an extent that you probably don't even need to cut that many points to be sufficiently protected against bias. This is only like 0.1, 0.2 sigma. And you can see here, these 3 ellipses correspond with these 3 vertical lines here, such that, again, green clearly biased from our true fiducial parameters, but that red is tighter constraints, despite because it cuts much fewer data points, while still probably sufficiently protected against bias. So this is promising to show that we can potentially cut fewer points than we have been in past analyses. But there's a lot of work left to do. Namely, as I already mentioned, we want to go to LSST forecasting instead to make recommendations for that survey. We'll test other cosmological models, ways to modify structure growth, like I've already mentioned. We'll also test various other ways to mitigate bias other than removing points according to this delta chi-square method. It's great that we can have a less strict threshold, but maybe there's a way to transform the data or add additional parameters to capture the behavior of nonlinear effects that would be more efficient potentially. And so in summary, for the problem we're trying to solve is that for non-standard cosmological models that modify structure growth, there's too often no validated tools to predict observables on scales with nonlinear density fluctuations. And we have developed the infrastructure to evaluate various methods to mitigate that bias, to find which method is best for upcoming cosmological surveys. And I think we should hopefully have time for a few questions at this point. And so I'm happy to respond to any you have. Thank you very much for listening.
How long does Ruben need to run before you have a
To be able to like do things with the results that we'll ultimately recommend? Probably that'll be part of the, well, correct me if I'm wrong, but I expect we won't do beyond lambda CDM analyses until we have the first full year of Ruben data. That first year of observation should start later this year, potentially by June, July. And then it'll take a year to do that first year of observations, about a year of post-processing. And so it's a little over 2 years from now that analysis will start. And obviously the standard lambda CDM analysis will be done first, and then the extensions analysis. And so it'll be a few years, so plenty of time to make recommendations.
other questions?
All right. Yeah. And I'll take the microphone as well. Okay. Easy to forget to do that, yeah.
Lena? HDMI or USB-C?
You can do HDMI.
Okay.
Ooh. Yeah. Right. Yeah. Everything is good. Okay. Cool. Great. I hope you can see my screen on there. I think it is. Oh wait, it's the presenter's view. Okay, why are we doing this? Why are we doing that? I want to share this. Share the slideshow.
Is there an option
That.
to...
Is that what? Ah, great, awesome. Yeah, not use this at all. Hi, my name is Alina. I'm a PhD candidate student at the University of Cincinnati, and I'm working with Dr. Matt Bayless, who just gave the first talk. He briefly mentioned what I'll be doing, but I want to thank you all for this opportunity to present here. My project that I've been working for about a year now is measuring spatially resolved nebula temperatures in high redshift galaxies. So a big goal of astrophysics is to formulate a broad framework for how galaxies evolve, how they grow, how they accrete mass, how stars form, how they form the heavier elements like beyond lithium. And one of the ways to do that is to look at the galaxy and look at the smaller parts of the galaxy to study the small parts like nebula gas regions that house these red dots that are star clusters. These star clusters act as ionizers, send out ionizing photons into the nebula gas and ionize the gas around the star clusters, that's the H2 regions. And we see the effect of this ionization as emission lines that we observe in the spectra. And we can study the physical properties of this nebular gas from these emission lines. And if we can study the properties of the nebular gas, we can understand what's going on there. And then from that, we can backtrack to understand what the star clusters do to cause that ionization. And we can study how they work together, the star clusters and the gas, to form the structure of the galaxy that we are studying. So the physical properties of nebula gas that I am interested in studying for my project is metallicity, which is just the chemical abundance in nebular gas. Particularly, we're looking at oxygen abundance, so that's the log over HO plus 12. And the other two quantities that I'm interested in studying is electron temperatures and electron densities, all of which are observed, all of which are measured using ratios of emission lines, various emission lines. And there are two main methods to measure these properties. The first one is strongline calibrations, and the second one is direct method. So I'll just talk a little bit about what those two are. So strongline calibrations use the ratios of bright nebular lines to hydrogen recombination lines to estimate the metallicities in H2 regions. So these are some of the common examples for strongline calibration ratios. These ratios assume that metallicity is a unique function of the strongline calibrations assume that the ratios are a unique function of the metallicity as a property alone, but in reality, these ratios are dependent on more properties like the dust attenuation, the density of the gas, the ionization properties of the gas. All that affects these ratios that we observe. And so due to that, these ratios are vulnerable to systematic uncertainties because of these degeneracies between the physical properties and the ratios of the lines. The other thing is the gas that we observe, the emission lines that we observe from the gas are not always just from H2 regions. They can also be from shocked gas around the regions like the diffuse ionized gas. So the fact of the matter is that when you measure strongline calibrations, you end up only getting scaling relationships to metallicities with lots of scatters due to these reasons, which isn't great. And the way to make that better is by measuring more lines. And that's what the direct method does. The direct method directly measures the electron temperatures using the ratios of temperature-sensitive auroral lines to a bright nebular line of the same ion for that ionic zone. And we know that these temperatures are sensitive to metallicity. So when the idea is that when there's a lot of metals, the metallicity is high, it causes cooling in the gases, and so temperatures go down. And that's a good thing for us to know. And one of the most common line ratios that we use to measure temperatures is oxygen 3, so triply ionized oxygen. The ratios of the faint auroral line 4363 to a bright nebular line 5008. Now, if you put together the strongline calibrations that I talked about previously and the direct method, you get empirical calibrations, which provide tighter constraints on the measurements of these nebular properties. So this plot here is for a work by Kurdi et al. In 2020. These are empirical calibrations using these some of these common strongline calibration ratios for some local galaxies, where the green stars are for the spectra of galaxies, whereas these circles are for stacked spectra. But just as a preview, you can already see there's some scatter here. Even though there's a fit line, there is definitely some scatter, and I will talk about why that exists shortly. The problem is when we start wanting to use these empirical calibrations at high redshifts. So at low redshifts, these galaxies are close enough to us that we can directly take their spectra. We can measure these faint auroral lines using ground-based telescopes. But at high redshifts, we need JWST to be able to do that, because it's so far, we can't measure its faint auroral lines without that resolving power that JWST has. And so several groups like Aurora and Cecilia are using the integrated spectra to make these empirical calibrations at high redshifts. So this is Aurora's work, most recent work, between redshifts of 1.4 to 7.2. And these are, again, using some of the common calibration ratios. But you can notice here the spread, the scatter is increased from the previous low redshift galaxy calibrations. And this is because there are several systematic uncertainties that come up when we use these integrated spectra. The first big challenge, or the big issue for why we have these uncertainties, is that integrated spectra use the spectra of the entire galaxy. And when you do that, you make the assumption that the galaxy is made up of homogeneous H2 regions. But that is not actually true. A galaxy has widely varying properties between its H2 regions. And Cameron et al. In their 2023 paper for simulation show that for a toy model of a nebular gas cloud with fluctuating temperatures of whether it's log normally fluctuating or Gaussian fluctuation of temperatures, even when you use the direct method, which is supposed to be the best way to measure temperatures, you systematically underpredict metallicity, as you can see here. And that is a problem. And this is where strong gravitational lensing comes to save the day, because it can now go in and strong gravitational lensing leads to bright magnified galaxies. So you can now go in and look at individual H2 regions and get their spectra. And particularly for my project, we'll be looking at spectra for galaxies from cosmic noon. So that's redshift 1 to 4. The other thing is, even when you do these these empirical calibrations for high redshift galaxies using their individual H2 regions, there's still some scatter, mainly because these galaxies are at the peak of their star formation. So this here is an example of a work in prep by a collaborator, where these blue dots and the purple dots are for a high redshift galaxy at redshift of 1.33. So the dark blue dots are for regions of the galaxy that have real H2 emissions, and the light blue are just emissions from regions that they believe are not H2 but closer to being diffuse ionized gas. The way they separate that is by just putting a signal to noise cut, and so that's why you can see there's the H2, what they believe to be H2 is clustered together at higher metallicity, whereas the diffuse ionized gas areas have much more scatter. But then when you take an average, an integrated spectra of that galaxy, and you plot that, that does fall on the empirical calibrations that were previously calibrated for low redshifts. So we want to really address this issue of the scatter that happens when you look at the individual regions, and that is where my project comes in as part of this collaboration, where we use spatially resolved spectra for multiple cosmic noon galaxies. This is just an example of one galaxy. We already noticed that there's a problem, so we want to do this for a large suite of them to measure direct temperatures, and then hopefully contribute to understanding why the scatter happens and how we can reduce the scatter in empirical calibrations. So this is the data I have. It's basically 9 cosmic noon galaxies that are brightly lensed and magnified. So that's what these are. You can see the arcs. You don't have to try to read this table. It's quite cluttered. The point is, what I'm trying to make is that there's a lot of faint and bright auroral lines that you can measure. And this is just some of them over there. The data that I'm using is from JWST's NearSpec. Just for people who may not have seen this before, it's available as data cubes. So that means you have 2 spatial dimensions and 1 spectral dimension. Here is the galaxy that I've started my work with. It's SGAS 1050. It's a brightly lensed cosmic noon galaxy at 3.625 redshift. So this is that here as an arc. You can see here the individual clumps. And because of how much resolving power JWST has, we are able to go and get spectra from each of these clumps. So this clump here with the pink circle, this is the spectrum just for that clump. And you can actually see that other than just these really bright lines, we're also able to zoom in and get the faint emission lines. So 4364, silicon 316, 6313, those are like faint auroral lines, which are really important in measuring temperatures. And now you can actually measure them at a good enough signal to noise ratio, signal to noise, that we can do something with that flux information. So that's what I've been working with. Sort of a preliminary result is that I have now been able to make a map of the ratios of 4363 to 5008. This is not a very good map yet. It needs a lot more correction. I've tried to mask out things, but you can see there are some bright spots here that are definitely not part of the galaxy. Those are some sort of hot pixels, some noise that has not been corrected. But we found that the flux ratio is approximately between 0.01 to 0.06-ish, which corresponds to a temperature range of about 12,000 to 30,000 Kelvin. So this is the fact is that this galaxy is tracing out really high energy gas, and that is really incredible. And the fact that we're able to like really look at these and see these hot knots there, that's really cool. And as I mentioned, noise is a big problem because you can see there's some bright spots here that are not part of the galaxy, that just is some hot pixels, some random noise. And that's also something that I've been dedicating a lot of my time to, is going through and picking up, really learning what the noise is in the background and constraining that, and using a code by a collaborator called Byron Sweep to custom reject outliers using Sigma clipping. And that's what I've been dedicating a lot of my time to, with some success, but this is an ongoing process. So my next steps for my project is to complete removing these outliers so I can get better temperature maps and get better ratios of these temperature and density line ratios. And I'll be using PineUp to actually measure these temperatures and densities, and we will be extracting these spectra from the pixels to make these temperature density maps, and do this for all 8 of the galaxies that we have. And in summary, what we want to do is measure these temperatures and hopefully contribute to reducing the scatter in empirical calibrations for high redshift galaxies. We'll take any questions now. Yes. Yes, it is something that we want to do as part of a theoretical aspect, because we have part of our collaboration, there's a group that works with the star clusters that cause the ionization. So if we can, once we get the data from them, and once I have done the part of measuring the temperatures for the H2 gases, the idea is that we want to take the spectra from them and use that as input parameters to see if we can recreate the spectra that we observe. That'll be an interesting thing to see. Yes, that is, we want to do that, yes.
Other questions for Alina? You mentioned the possibility of archival data, HST archival data. How many galaxies that would roughly add to your sample?
So the archival data that I referred to are for these particular galaxies, but we are, in the future, if we can get JWST data for some of the other archival data that we have HST for, it would be great, but we won't be working with that until we can.
Thank you, Alina, again.
Cool. Yep.
Can you stop sharing?
Yes, it is.
Cool. Communication line or both? Okay. Easier.
And then are you sharing your screen? Not yet. Nothing. Actually, here, let me try this. And then I have to stop extending this. All right. All
All right. Hi, everybody. I'm Cole. I am also a student with Matt Bayless, the guy we saw just a little bit ago. My project here is to try to understand a little bit better about the extreme high energy sources in the early galaxies of the universe. Let's see. All right. So I think we've all seen a plot like this before. But in case you haven't, I mean, we see where we go from the Big Bang to basically now how the galaxy or the universe has evolved. And so we see in purple here the epoch ionization, and that's kind of because that is the kind of the phase shift time period between when we've gone from more of a neutral IgM neutral universe to the ionized state that we're in now. And we know that Lyman continuum photons are the ones that had to have been the things that had to have done the ionizing, because they're the photons that have enough energy to ionize. Now, the escape of these photons from these galaxies is crucial to understand how these processes occurred, but we can't exactly measure them directly in the epoch ionization because they're blocked. You know, they get absorbed by the neutral hydrogen that exists in that time frame. So that means we need these indirect probes of Lyman continuum emission that studies at less than Z of approximately 5, but also a little bit, you know, can't exactly be super close because they'd get absorbed in the Milky Way as well. All right, so kind of to get things kicked off here, reionization requires us to have the volumetric rate of the Lyman continuum photons entering the IgM overcome the recombination rate of the ionized hydrogen. And so N dot ion here is kind of is that volumetric rate. And each of these pieces here are kind of important features that different collaborations or different people are trying to plug into that. So F escape here is the Lyman continuum escape fraction, so the fraction of the photons that are actually getting out of galaxies after they've been produced. Psi ion, the production efficiency of these photons, and then UV luminosity density, which is not exactly something that our group works on, but is something that is highly constrained by other groups. But let's talk about psi ion a little bit. So that one is a critical quantity because it relates to the number of ionizing photons produced in a galaxy, like I mentioned. It is given by this Q over LUV, where LUV is just a reference luminosity, generally taken at about 1500 angstroms. But Q is the ionizing photon production rate, so that's kind of the critical quantity here. We're basically looking at the area under the curve here by doing an integral of that over the whole ionizing range, which is up to 912 angstroms there. Now, of course, to have it be the right units to divide by the energy of a photon in there as well, but that's kind of the general idea. Now, psi ion is something that we can very easily probe using, or look at, and is interesting with these extreme stars, like I mentioned before. So these extreme stars are the ones that are basically giving up almost all of the Lyman continuum emission that we see. It's something that the sun is unable to do. You know, it's not big enough. It doesn't give off as much energy, so they're way more extreme than the sun than we have. As kind of evidenced by this plot here, we see these are all different stellar populations. We see at different ages. These are in millions of years, and Z scaled by the metallicity of the sun. These three up here show a lot more Lyman continuum emission in this gray shaded region. These are young stellar populations, only a couple million years old. So all the extreme stars are still around and emitting a lot of high energy photons. But by 40 million years, we see that basically goes away, right? And so this tells us that, you know, we're really focused on these extreme stars, that they must be the biggest drivers of this reionization. And something that they also do is this feedback process. Now, over the course of their lifetime, they're able to clear out gas and impart enough momentum, almost as much as a supernova would, of course, in a much shorter time scale. But yeah, so we see that these are short-lived. We see that they're rare. But since they have such high Lyman continuum emission, they're pretty much the main thing that we're looking at here. And so one of the probes that, and I've said indirect probe before, we're looking at a number of different emission line properties for this. And now carbon-4 is kind of the main one that I'm looking at. It comes from massive stars, comes from AGN, comes from even stellar winds. The stellar winds one would be more like Wolf-Rayet stars, would get broad emission from that. We're not focused on that one. We're worried more about nebular carbon-4 emission, which is much more narrow peaks for that. Now, carbon-4, what even is that? It's triply ionized carbon. It has a doublet around 1550 angstroms. but has a really high ionization energy relative to hydrogen. Like I mentioned, that means we see a lot of lime continuum emission if you see a lot of strong carbon-4. And so we can learn about Xi-ion if we know about carbon-4, basically. Carbon-4 is also a resonant line or resonant doublet, which means that it scatters a lot in gas and highly ionized regions, and so it's sensitive to those gas conditions and can tell you even about F escape. Now the other thing here is that we see on the plot over here that AGN basically, well, the plot is showing star formation or star forming regions, and so we see that they kind of decrease as we go to higher energies. Now AGN are more like a power law, and they go up in that time frame. And so we can see how some of these different diagnostics could tell us about what type of sources we're looking at. And so that's what we see here. We see how carbon-4 in combination with helium-2 and carbon-3 is able to differentiate very well between different ionizing sources like AGN or star-forming galaxies. Now, in theory, even the carbon-4 itself, the ratio between the two, the doublet, is supposed to be about 2. And so if you even measure that, you can even learn something there by knowing about the little attenuation that might be along the line of sight and low column density as well. Now we do have 2 carbon-4 emitters that I'm more focused on and doing data or doing analysis with, and those would kind of line up in about this region over here. Now RCS 0327 lines up pretty well. We have a little bit more resolution of all 3 of these lines. Now we don't exactly have a great showing for helium-2 here, as it's right under a skyline. These are ground-based spectroscopy, so we're able to kind of corner it into this little area up there. We know that it's star forming though, based off of the carbon-4 and carbon-3 that we see. The reason why these 2 are really nice is that they both have strong carbon-4 and are Z less than 5, which means that Lima continuum should be accessible. We should be able to learn something from this. So zooming in, and most of what I've been focused on recently is with SKS 1152. We can see the profiles of both carbon-4 and Lyman alpha, that they're both double peaked, which is fairly standard for resonant lines like both of these, because low density or outflowing gas can up and down scatter these photons. But we can learn something from this, because the smaller the peak separation is for, let's say, Lyman alpha, the lower the column density and the larger the fraction of escaping Lyman alpha or Lyman continuum photons. And so that tells us, that's one of the quantities that we want to know about. And even not just the separation, but also the ratio just between the blue peak and the red peak themselves can also correlate to this F escape. And so we're going to do both of those and see how those bear out. The delta V, the peak separations for Lyman alpha, though, they don't trace the same gas as carbon-4, right? Because Lyman alpha resonantly scatters in neutral hydrogen, so it's a lower energy region, and carbon-4 resonantly scatters in really highly ionized regions because it takes really high energy to even get to that point. And so we know that they must be tracing different regions, tracing different gas conditions, and so we can learn something about the radiative transfer differences between these as well. So the next kind of steps that we're going along here is try to develop a new framework for maximizing the spectra that we have, try to see if we can't get the helium-2 line out of the one spectra that I showed you. That's kind of ongoing. We're trying to get that better. So that way we can measure these line fluxes a little bit better. So that way we can more narrow down on that plot that I showed you where our carbon-4 emitters would be, but also where they would line up in amongst a bunch of other emission line diagnostics, which I didn't show, but there's a lot of them. The double peak profile also is very interesting. We can learn about column density and F escape, and also the radiative transfer differences between the 2 regions of ionized gas and helium or hydrogen as well. So that can tell us a number of things. That's all. Thank you.
You mentioned that your so you figured they were ground-based instrument.
Gemini.
Gemini?
Yes. Yeah.
Have you put any kind of proposals or anything like that for space-based?
I know there have been proposals for JBOST. We haven't got one accepted yet. So.
All right, let's thank Cole again. Can you stop sharing?
Yes.
And then for our last session, or for our last talk of this session, this is something that we've done in the past, and I don't know whether it's torture or whether it's a good opportunity. But for anybody who's doing a poster, for anybody who's doing a poster, if they would like to come up and give like a 1-minute kind of preview of what their poster contains, just so that we will be enticed to come talk to you during the poster session, you are more than welcome to do so. Of course, nobody is going to be forced to do so. And so is there any poster presenters who would like to lead off and give a short description of what your poster will be? Be sure to give your name and where you're from.
Hello.
You're fine.
Hey, so and I'm from Northern Kentucky University, and I worked with Grace Fireman, Amara Baptiste, and Grace Manganoza, and our faculty mentor was Dr. Dirk Grupa. And we put together a poster on the long-term variability of AGN. We did find a anti-correlation with variability and mass of the AGN. And then Trevor will later be giving a talk that's kind of similar to ours about the short-term variability of AGN. So we're all looking forward to that. So.
Hello, I'm Jacob Canada. I'm also from Northern Kentucky University, and I worked with Dr. Nathan DeLee, who's also there, to make a radial velocity stable catalog using data from SCSS. So we did 2 different data sets from 2 different phases of the survey, and that's pretty much all I have, but I'd like for you guys to come and check it out.
And Dr. DeLee didn't even let you off class today. Is that true? I know, that's hard.
Yeah. Hello, everybody. Is this thing on? Yeah? Okay. My name is Cole Miller, and I'm here presenting my poster, a statistical study of rebrightening in major solar flare ribbons. So solar flares are among some of the most powerful events in the solar system, wherein immense amounts of energy are released from the sun. During this process, the surface of the sun is actually brightening up, and that brightening we call the ribbon. So in this study, we look at that morphology over time, and we detect a pattern called rebrightening, wherein the pixels in the ribbon data brighten up multiple times, and we analyze this statistically to characterize the behavior. And then furthermore, we actually correlate it to the eruptivity of the associated flare. So that's my poster.
Hi everyone, I'm Nikhil and I'm from University of Louisville. I joined last fall and I'm working with Professor Bene. The poster that I have back in the session is on modeling surface features of young stellar objects using Tesla light curves. So the basic concept is that we all know our sun has spots, more equatorial spots. So what about stars that are distant enough? How can we measure the location of stars that are distant away, and specifically we look for cases for young stellar objects. So feel free to come over there. Thank you so much.
Hi, my name is Evan Jennerjohn. I'm a PhD candidate at Ohio State, and I lead the Assassin Low Surface Brightness Survey there. For those of you who aren't familiar with Assassin, it's a time domain survey that's been running for a little over a decade. We have telescopes all over the globe that take a snapshot of the entire sky every single night. And so that's mostly used for looking for like variable stars, looking for supernovae, but I don't do any of that. What I do instead is I take that 10 years worth of data that we have, it's all in the G-band, and I stack it on top of each other and get really high signal to noise, and then I search the sky for faint stuff, anything that's low surface brightness. So if any of you are interested in looking for faint things, please come talk to me.
I'm William Keener, a senior undergraduate at Austin Peay State University. I'm presenting on the Lyman alpha ratio. Astronomers tend to assume that it's 2, but there are conditions under which it deviates from that, especially at high densities, and well, we only see it at high temperatures for heavy ions. Specifically, I'm looking at the iron Lyman alpha ratio. And we also go over a few ionization balance states to see how that rate of drop off from the ratio evolves.
Hello, I'm Ben Herman Holt. I'm from Western Kentucky University. I'm in my master's program there, and I'm studying the emission lines of hydrogen in cold clouds of gas in the interstellar medium to see how they form stars.
Hi, I'm Cameron. I'm from the University of Cincinnati. I have a poster on analyzing neutral hydrogen scaling relations in the high frequency spectral window of the Laduma catalog. Mine is the huge poster that I accidentally made way too big, so I want to apologize for that now. Yeah, I know, it's the painfully large one, but happy to check it out. Thanks.
Hello, my name is Erin and I'm from The Ohio State University, and I'm presenting a poster on some work that I did last semester and last summer. Specifically, I estimated the radii of over 50,000 stars in the galactic bulge.
Anyone else?
Hi, I'm Allie Chris. I think this is working. I'm a postdoc at Ohio State, and I'm basically here to make microlensing for planets seem less unapproachable and grumpy. So I have a big billboard poster for doing the microlensing data challenge.
Anybody else? All right. So I apologize to some of the speakers for the mowing that happened. I mean, we're in no control over when that actually happens. Go figure. And it happened right during that session. But I think everybody can still hear okay. So we're ready for our first break. This one is a little bit shorter. It's only 15 minutes. Coffee and water, as a reminder, are here, and then other drinks and snacks are over in the other building, and that is also where the posters will be. And so 15-minute break. We'll reconvene right about 1:45. Thank you all very much.